So we're going to talk about what's called the common ion effect, which again, common ion, what ion do things have in common? Now what happens if I put things together that have that common ion? So, my first bullet point is dealing with what you just worked with, milk of magnesia. Very common for a common ion problem, and it starts with just this first part, and then it goes into a second part like below. So I'm going to kind of go over both parts here. Let's see if I can just continue this, if I have enough room here. But here's my milk of magnesia, my magnesium hydroxide. And remember, at equilibrium, we would designate the concentration of magnesium to be X, and of the hydroxide to be 2X, because there's a 2 coefficient in front of it. And this first bullet point is hopefully a review of what we did last class period. Because then what you would do is set these things equal to the K value. Now remember, when we would set this up, it'd be X times 2X squared, because we always have to raise it to its stoichiometric coefficient. X times 2X squared equals 2.06 times 10 to the negative 13. This is the same as 4X cubed. So if I divide by 4, if I take the cubed root, I get 3.72 times 10 to the negative 5th molar. Again, recall what that means. That is the concentration of the magnesium ion, or we could say in general of magnesium hydroxide solution, because it's a 1-to-1 ratio between the magnesium and the magnesium hydroxide. If I were to ask you about the hydroxide concentration, you would have to plug it back in. It would be twice as much. Now, part 2. What would the solubility of magnesium hydroxide be if it was trying to be dissolved in a sodium hydroxide solution? Because this is towards the bottom of the slide, I'm going to go to the Smart Notebook for the second part, just to hopefully make it a little bit easier for you guys to see what I'm writing down here. But start off with the same solubility equation as before. Except for this time I'm not going to cheat my ice table like I did before, where I just put down X and 2X and there's nothing. And the reason why I'm not going to cheat it is this question gave me an initial concentration of sodium hydroxide of 0.150. That's important because within sodium hydroxide, there's sodium, which when I look up at this equation, I could care less about sodium. And there's hydroxide. When I look up this equation, I do care about hydroxide. This is the little twist that we have to learn today. That first part, okay, how do I solve magnesium hydroxide dissolved in water? No big whoop. But what if I'm trying to dissolve it in a solution that already exists? Quite frankly, again, this is kind of what I do with the semester project. When I mix different ions together in that test tube and I give it to Chem 1 students, I got to make sure first off that they're not things that are going to precipitate. By the way, I could solve that semester project in like 4 guesses without doing a single test. As long as you could tell me which ions I have wrong and when, because I would know which things can dissolve and can't dissolve together. So if you know your chemistry, it's not that rough. Again, we still would use our X and our 2X here. But what makes this problem different is that our expression is a little more complicated at equilibrium for one thing because it's already in presence of a whole bunch of acid ions. If I were to set this equal to K, what was K again? 2.06 times 10 to the negative 13th. All right, let's stop for a second and evaluate what we have. This problem here looks like it would be a lot more difficult to solve than the previous problem. I know how to divide by 4 in a calculator. I could take the cubed root of whatever's left over in the calculator. But when you look at this one here, I first would have to factor out all of this. And then I have to multiply it by x. And that would give me an expression that's going to include a 4x cubed, I don't know, it looks like a 0.6x squared, and whatever this squared times x would be. It's going to get me a pain in the butt, right? And what we've told you before is when you see expressions that you recognize of, oh, I don't want to do that math, there's ways that we can go around it. One option is, can we take the square root of both sides? Not really, because this one variable in front kind of prevents it. I mean, this guy, yeah, but that x in front doesn't work very well. When you have a tiny k value, so 10 to the negative 13th, that means that it does not create much of the ion, right? Compare that number, that 3.72 times 10 to the negative 5th, to 0.150. Even if I were to double the 3 point whatever number from the previous times 10 to the negative 5th, if I add that to 0.150, it's not going to change this much. And that's where you were taught last week of the idea of using an approximation. That typically what happens in a common ion problem is you are asked, how much can you dissolve? And you are given a fairly large concentration of one of the ions to start with. Which is when you look at this expression then, what you need to realize is if you add plus 2x to 0.15, and that 2x is a ridiculously small number, we can just as easily cancel it out. That's the approximation that is suggested from our text, from the College Board. Because now what I have is x times 0.150 squared equals my k value. Now I have something algebraically that we should be able to solve. And that x value then, after I square that and divide both sides by it, would be 9.16 times 10 to the negative 12 molar. This should make sense, that this is less soluble than magnesium hydroxide in water. Because again, in this second problem, you already have OH present. And if you already have OH present, think about it in terms of Le Chatelier's principle. Unlike what we just did in the lab where we took away hydroxide, if you start with hydroxide, equilibrium is going to shift that way, meaning everything is going to be less soluble. Again, when I look back at our goal sheet, we're right there, it even uses the fact that you can use Le Chatelier's principle to figure it out, or you can solve with KSP. And that's what this last goal is trying to get us to recognize, is that there is two ways to see that it is less soluble now. We could think about it in terms of Le Chatelier's, but we can give an actual quantity by doing this type of math. As I said before, the last slide that I have, there's 2 practice problems in the book that I would suggest you kind of looking at to go over this. After that, work on the reading guide, which is going to be a review of all of this KSP stuff, which is early KSP. It's what I just did here, and it's that double displacement problem that I put up on the board as well using K. Now, if you get done with all that and you have time to spare, there's other practice sheets that you picked up that you can work on as well. Heck, one was a old AP question from like 2004 that you can do. Otherwise, this is our day to kind of wrap up all that KSP stuff.